Hello, today we are going to discuss how to combine two ideas that we have already discussed. One is the spring lever model or SL model, the other is the feasibility map. Spring lever model is a model for compliant mechanisms, so that you can treat compliant mechanisms as a terminal characteristic model, where there is just input output stiffness there, and of course, the intrinsic ratio n, KCI, KCO are the stiffness parameters and n is the lever ratio. And we also discussed in the last lecture how to construct the feasibility map. Feasibility map captures the user specifications in a visual way. So, user can see how stringent the requirements are or how loose the requirements are, whether the requirements are possible to have a mechanism. Right. Today these two ideas will combine together to create what we can call a selection map technique for designing compliant mechanisms. So, let us look at how we do it. So, beginning with the selection and redesign. So, here the keywords are selection, redesign of a compliant mechanism. Not only we can select a compliant mechanism from database, but we can also redesign as per the user specifications, which is captured here with the help of the feasibility maps. So, to recapitulate what we have discussed in the last two lectures, one is this spring lever model and the other is the feasibility map. Okay. What did we learn in spring lever model? We learned that by doing two finite element analysis, this will be finite element analysis 1, this is the first FEA, where we apply force here, this is F input there to the compliant mechanism, and we record the input displacement XIN. So, whatever displacement you get here, let us call this XIN, and we also measure the output displacement. In this case, output displacement will be like that, let us call this X out. Then as shown here, the KCI input side stiffness can be obtained as Fin divided by Xn, that is what is written here in smaller print. And N here, this is N, which is X out divided by Xn, which would have measured from the finite element analysis. So, that is one where we got KCI and N. In order to compute KCO, we remove the input force, instead we apply output force in the direction or in the opposite direction, whichever way you want to do. We apply the F out and record the input displacement as well as output displacement. So, there will be, we are using a different symbol now, instead of X we use Y, and there will also be a Y in here. We put these two together to get KCO, which is output side stiffness, that is given by F out divided by Y out minus N times, which you have calculated in the previous step. We will get F out divided by Y out minus N Y in will give us KCO also. So, these three parameters capture the static behavior of a compliant mechanism. And then we also discussed how we can take user inputs on 6 parameters. They are the input variables, that is F in, U in, input force, input displacement, F out, U out, output force, output displacement, and actuator stiffness Ka, and we also had K external, that is external object stiffness. From those we find the feasible values of KCI, N and KCO, different sets, that gives us the feasibility map. This is the 3-dimensional map of the feasible values of these parameters. If you project that, we get a 2D map that is plotted with KCI and KCO. So, these are basically a reflection of the user parameters, user inputs with lower and upper bound on 6 variables. Now, we have these two complementary ideas. We say the ideas are complementary because what one has other does not. So, we have SL model for compliant mechanisms. This is a reflection or abstraction of the compliant mechanism. Every compliant mechanism has a unique set of values for KCI, KC1, N. These are like, as we already said, terminal characteristics, they are properties of compliant mechanism. Now, we have the complementary idea, which is a reflection of the user specifications. They are all specified by the user, it has nothing to do with compliant mechanisms. Now, these two complementary ideas we put together into one idea. Before we do that, we need a third idea, and that is called Ashby maps. So, this is Michael Ashby at University of Cambridge, who has developed this for material selection. What is shown here is on the x axis we have density, on the y axis we have, in this particular case, we have compressive strength. In fact, in the Ashby map technique, you can take any two properties and plot them in a plot like this. Usually it will be a log plot, because here it is 0.1 gram per centimeter cube, this is gram per centimeter cube, and this is in gigapascal, and of course it is log scale, because gram per centimeter, this is 0.1 and this is 1 and this is 10 log scale. Similarly, this is 0.01, this is 0.1, this is 1, this is 10 and this is 100. Okay, it is a log scale. What does it show? It shows all materials that are possible, that exist. So, for example, there are polymers here, metals and alloys, graphite, or all kinds of things. So, if you plot like this, similar materials occupy a space in this map. Okay. So, you have compressive strength and density for every material, then it will give you an aluminum alloy, right. There is a point there, there is a point there, point there. Combining all of them, you get this big orange shape, which contains all aluminum alloys. Densities, compressive strengths have ranges, and you get this, right. So, here we are looking at the properties of materials and plot all the materials and then see. So, there are woods here, there are some silicon nitride, diamond, all kinds of things. They are in this map. We show their relative positioning with respect to the pair of particles that are considered. In this case, mass density and compressive strength. Okay. So, this way we can plot all the materials, and Ashby says once you have this, you will have some criteria based on your design requirements, and that will have what is called a material index. He talks about a material index based on a performance criterion that one would want. In this particular case, we have two material properties, density and compressive strength. Let us say compressive strength is denoted by sigma, density is divided by rho. It need not be just sigma by rho or sigma rho, there can be an exponent there, an exponent here. Okay. When you have something like this, you would say that if you maximize this material index, then your performance criterion is maximized or minimized, whichever way it is. Then what you do is, in this map, since in log plot, this alpha and beta amounts to basically a straight line. When you write this material index and take log of this, you will have 1 minus alpha times log sigma minus beta times log rho, and that will be a straight line here. So, one will be in terms of the other. So, if I do log of this, I will get alpha log sigma minus beta log rho. So, I can write log sigma here, in that case log sigma equal to beta log rho, and then it will be 1 over alpha. So, it will be divided by alpha, right, and there could be some constant as well, if depending on what all you have in the performance criterion. So, basically between log sigma and log rho, you have a linear relationship, you get a straight line. So, what you have here, it could be sigma by rho will have one slope and sigma by rho raised to 2 over 3 has another slope, and sigma by rho raised to half is a third slope. So, we have different curves here. So, let us say we take one curve, let us say this is parallel to sigma by rho. So, if I want to maximize sigma by rho, I basically move this line. So, I can draw a lot of lines parallel to it, and I can see extreme is here. So, maybe diamond is the best material for it, or if I go further, there is some graphene 24 or carbon nanotubes over here, right. So, you see that they are the best in terms of compressive strength and density. What are the worst? You come all the way here, and whatever materials are there, they become the worst ones or the one that minimizes material index. So, by putting all materials in terms of this map, we can select material. Okay. So, that to reinforce idea, now we have here again two properties. One is density for a different criterion, the density, and here we have Young's modulus. We have Young's modulus. Again, you can see how the materials cluster together. So, there are natural materials over there, some foams, elastomers, polymers, composites, metals and alloys, ceramics, they are all occupying different spaces. But if you have material index, in this case it is E by rho, okay, then you draw a lot of parallel lines and you get the best material E by rho there, that has one value, one extreme, other extreme is here. So, based on the extreme values you can choose materials, but idea is properties can be shown on a map, so that materials can be compared with one another, and the best material, either the best extreme or worst extreme. When I say worst, it could be minimization, that is still the best when you want to minimize, or the other extreme where you maximize, and that is the best for you. So, that is how Ashby's map method works. We use this third idea of Ashby's map and put it all together. So, idea is now the feasibility map that we have, the feasibility map here that we have drawn, that comes from user specifications, that comes from user specifications. We discussed in the last lecture how that can be computed by solving two equations and 12 inequalities, upper and lower bounds on the 6 input parameters. You draw the feasibility map. Now, we also know that every compliant mechanism will also have unique values of KCI, KCO and N. Okay. Now, what we do is we put those compliant mechanisms in this chart. Now, we have KCI here and then KCO here, and this is a feasibility map projected. We are not showing N, N is shown like a gray scale here. So, N is shown on a gray scale. On this map now, like in Ashby's map, we put all these dots. So, each one of them corresponds to its KCI, KCO, every one of them. So, for the example, this will have some KCO there, some KCI. They are the coordinates, we put them. If feasibility map like a country's map, all these mechanisms are like cities in it. Now, the idea is very simple. In order to select a compliant mechanism, you just see which of these compliant mechanism dots, that is each dot corresponds to a compliant mechanism. This is A, this point is, let us say, compliant mechanism 1, and this is compliant mechanism 2, this is compliant mechanism 3 and so forth. Whichever is lying inside the user specifications based feasibility map, then we say that compliant mechanism, that compliant mechanism satisfies the user requirements. In this particular case, this is CM1, CM1 is inside, CM1 satisfies user specifications. That is what we can specifications, we can conclude here. So, it is as simple as that. So, we have a map in which we are superimposing the feasibility map and compliant mechanisms. Again, remember that each dot corresponds to a unique compliant mechanism. There could be other compliant mechanisms also, but corresponding to each dot there is a compliant mechanism. I do not say unique, because two compliant mechanisms can have the same values of KCI, KCO and N. Okay. Now, when we are inside, when we say inside, it is not enough to be inside in this 2D projection of KCI, KCO map, the N value should also match, in terms of grayscale level also it should match, in which case you take that compliant mechanism and walk away, because you have selected a compliant mechanism that satisfies the user specifications. Do we say this is the best? We do not say, we only say that it satisfies the requirements. If the user wishes, user specification can be tightened or changed and then see how the compliant that is chosen now would fare. But even then we cannot say it is the best, it is just the one that meets the specification. It is a different design philosophy. Here user specifies what he or she wants, and then we draw this map by computing, that is solving the inequalities and equations. Then we superimposed on it a number of compliant that we have in a database, and we have, I will show. We have all these compliant mechanisms in the database, and they all can be shown whichever lies inside, where not only KCI, KCO, but also N value matches, that is the one that is selected, and one can move on with that. That is the principle where we are superimposing two concepts, rather Ashby's map concept as well as feasibility map and SL model concept. So, typically this is how it looks, and what we can call now a selection map, where we have KCI and KCO. This is KCO and this is KCI for some specification, input force some 100 to 50, and there is 0.001 to 0.002 for displacements and so forth, output force, output displacement, stiffness at input, that is actuator stiffness, stiffness output, that is external stiffness, we can do all it, and then if you click show feasible map, then it will draw the map, and some of them are inside, some of them are outside, whatever dots that we have in the database, and we can ask the interactive software to show all the mechanisms, or you can say show only top 1, top 2 and so forth. How do we know what is top 1, top 2? Again the program computes how many mechanisms are inside, how many mechanisms are close, how many mechanisms are far off. That is how it would rank. What those are, things that are inside will get more weightage than things that are outside. Outside also, one that is closer to feasibility map is rated higher than something that is little farther, okay, or this may be the closest now, is a little farther, little farther, little more farther. So, we can see all this and choose the one. You can click on something, I want that, and we can select it and then see if the N value also matches. If it matches, then you have chosen or selected the mechanism. This is a MATLAB based software, you can see MATLAB icon here. So, you will get that software to play with, and we will explain more features of this. So, there are many other features. This is where we input, our user would input the requirements, that is F in, U in, F out, U out, actuator stiffness Ka and external stiffness, and then show the feasible map, show the mechanisms, and we can select a mechanism that we like and look at what material it is made of, and we can also learn about the maximum stress, that if there is a button here, if you press that it will show you what is the maximum stress, and you can learn a lot about the mechanism. There are few more things related to manufacturing aspects that we will discuss as we go along. So, now given a set of specifications, we draw the feasibility map and we show on the same map the compliant mechanism in the database as dots. If something is inside, N value also matches, then you take that and then say, yeah, my requirements are met. What if none of the mechanisms in the database are inside the map? What happens then? If they are not inside at all, that means that your specifications, because the map exists, then your specifications potentially have a solution, but none of them in the database meet your specifications. What do? then you can modify a mechanism that you like to match the specifications. So, here is an example. We have let us say only one that is outside, which I have circled with red color here, and that is not inside, all others are say let us say outside farther away. Okay. None of them are satisfying our requirement. So, they are all outside the feasibility map. Okay. Then we take the one that is closest, let us say this is the closest here, and then try to get it inside the feasible map. How do we get it? Not arbitrarily, but by modifying it or by redesigning it. What are all the things that we can redesign? There are a number of parameters for redesigning. One is the in plane width of the members. So, if you have a beam, there is in plane width, this width you can vary in the compliant. You do not change the size, just change the in plane width or thickness. So, it may have some thickness here. So, that thickness over here can also be varied, thickness can be varied, or size in x, size in y, or material, or all of them can be chosen, and then see how that changes the KCI KCON. That is, if you have a compliant mechanism and you change the width or thickness or material or the size can be changed in the x direction or it can be changed in the y direction or changed together x and y. So, when you do those things, a point that is outside right now will move, it may move, let us say I increase thickness, the point may move like that, because when mechanism is made thicker, its stiffness KCI, KCON will change, accordingly point will move, or it can go the other way, that is T minus. Similarly, you can have it for the width, you can have it for the size x, you can have size y, and you can have for the material change. That is how we can redesign it. There are a number of them, that is what is shown here. So, if I say T plus, that means that from where you are you will go like that, and T minus you are going the other way, and similarly Sx will go that way, Sx plus, Sx minus, that decrease in the size, increase in the size, decrease in the size, increase in the size in y direction, or you can change material and so forth. So, every point will have lot of options to go based on these parameters, and that is how we redesign. We do not change the topology, we do not change the shape, we only change the size, meaning x direction, y direction, and thickness and width, and material also. We can change all of them and then see how to get them inside the feasible space. Again, when I get some mechanism inside the feasible space, I also need to match n. It is not just KCI, KCO, but also n has to match. Here is a typical real example for redesigning paths. So, there is thickness and stretch x, stretch y, stretch x y, both simultaneously you can do, and how it looks, how you can go from one point to other points where you change these parameters. So, user can interactively explore what are all the possible things to get the mechanism inside the feasible space, so that we will again satisfy requirements, even though to begin with none of the compliant mechanism points are inside the feasibility map. When you do this resizing, let us say you are here, by resizing you are over there, what it means, let us say here we are resizing in both x and y, a mechanism that is like that big one may become small one, or small one may become big one. We are not changing anything else, changing the size and then see how our specifications are met. You can change in plane width. So, here this particular width is small, now here it is large. So, all the in plane widths are proportionately changed. So, we are not doing everything separately, widths are proportionately changed. Some of them, sometimes you may make the widths bigger, sometimes you make it narrower. Widths are proportionately changed. and the change effect of the change you can see in the map, because that point would move to another point depending on how the width is changed. It can be increased, it can be decreased. In doing so, we can take into account the diameter of the mill bit, or for that matter any manufacturing process that you are using, we can take the mill bit diameter and accordingly design the compliant mechanism or redesign the compliant mechanism. So, we have indicated over here in this program material, in this case polypropylene is indicated, and CNC and laser or the process that are load, we can look at that. And also once you choose a process, let us say you choose CNC machining, then minimum gap feature, minimum width feature, minimum thickness, maximum thickness, and minimum size and maximum size. All these parameters you can put in what can be done with that process. It can be laser, it can be CNC, then accordingly the mechanism design can be redone so that manufacturing aspects are obeyed. And we also said strength can be obeyed because there is a maximum stress, you can click that button any time and then see what the maximum stress in the mechanism is. So, this is the philosophy where you have the interactive thing where we can change, in this case this illustrates how the in plane width can be changed within that mill diameter. So, this is the mill bit, and based on that we do not want to increase the width to more than certain value, because in which case it will not be possible to with this mill, okay, if you make it really narrow, and it takes care of that. How large can you make, how small you can make based on the manufacturing process specifications. So, redesign procedure, again we are outside, let us say you have come in, and then if you go further you are going out of the map, but the n value does not change, you can take a different path and where the n value can be actually changed to meet the user specification, not just KCI KCO, n also has to match. In order to do this, what we need is a catalog of compliant mechanisms, that is every compliant mechanism should be shown as a dot in the feasibility map. For that we need to have a database of compliant mechanism, which we have. A number of years of research has led to a lot of designs. In our lab we have currently about 90 compliant mechanisms, each with its own individual topology, and they are all stored in either MATLAB program or a JavaScript. I will talk about it. So, we have a database of that. Every one of them has a KCI KCO n value that is put in and then shown as a point when the user comes, user's feasibility map is shown, user can bring a mechanism into the feasibility map if what are the inside the feasibility are not satisfied. You can look at the mechanism and then see whether you like it or not. Okay. So, a number of mechanisms that we have on the screen now. So, we have these 4 and we have many more and even more. Okay. We have about 100, target is 150, but there are as many compliant mechanisms around there, and we can put them all at the disposal of the user who does not need to know much about compliant mechanism, can still select what is needed or redesign if the selection is not good enough. So, overall view of this procedure is that we start with the user specifications. Right now we are talking only statics. So, force, displacement, the input and output, actuator stiffness and external spring constant, that is to model the workpiece with which compliant mechanism is interacting with. And of course, there are a few more here which apply to dynamic characteristics, which we will discuss later. We saw the governing equations, which we had 2, and we have these SL parameters that we can put for each compliant mechanism. Each input specification has upper lower bounds, we use that to get this feasibility map, and then we get this SL parameter ranges and show them, and compliant mechanism database will show all the mechanisms, and then we can draw the parameter curves to bring a mechanism into the feasibility map to satisfy the user specification. So, redesign parameters are provided, manufacturing constraints can be incorporated, and maximum stress indicated all the time. Press a button, it will show you what maximum stress in the design is. That means that inside this user interface there is fire and element analysis running all the time. Once you choose a mechanism, we can actually create an IGEST file and actually go to manufacturing thing readily. So, it is a very pragmatic design where you actually select and redesign if what is selected is not good enough. So, it looks somewhat like this, where we have a feasibility map which is shown in this red here in green color here. This is all the feasibility map, and here the point happened to lie outside. Let us assume that there is nothing else, and we draw this in plane width increased. So, it will go like that, in plane width decreased will go like this, and thickness increased goes like this, thickness decreased goes like this. So, that way we can bring it into the map, meaning that you are modifying the compliant mechanism that is close to the feasibility map to come inside the feasibility map, so that N also matches. This is an interactive redesign program, and it looks like this. We also have a Java version which is the URL given here. So, you will be able to play with that also in Java. You can just run it, and you can see that we also show the mechanism. In fact, if you click some of these, you can also see the animation of the mechanism. So, the philosophy of this method is that user does not necessarily know where the input and output point should be. They just know between input output what kind of behavior is needed, but we do not say orient this way. On the other hand, where the user sees the mechanism or looks at the animation simulation of that, or even a video of a real mechanism that is in the database, then user can decide whether that is good enough for the application or not. Okay. If it is not, they can go for the other one, because there are number of them that are close by, and the one that they pick is the best one. They look at the manufacturing parameters and then redesign if necessary, and finally be happy with the mechanism because it satisfies the user requirements. So, here this is also the Java based one, where you can see real example where the feasibility map is this little thing. We can zoom in and out and all that is possible, and you can draw the parameter curves and see the mechanism, and we can actually see reference also which mechanism it is, which paper it is taken from, and manufacturing parameters, and finally we can choose a manufacturing process, and for that we can check whether the mechanism satisfies all the requirements. So, the main points of this lecture is that we have combined the spring lever model, feasibility map and Ashby map together to create what can be called selection maps. We also discussed how a compliant mechanism that is reasonably close to the feasibility map can be redesigned to actually satisfy the user requirements. We can incorporate manufacturing considerations such as minimum feature size, maximum feature size and so forth. And finally, this whole thing is interactive program where you can select or we can redesign. And these two papers by Sudarshan Hegde in General Mechanical Design and Mechanism Machine Theory are the references to read further. In the next lecture, we will consider a couple of case studies to illustrate how this method works. Thank you very much.